Okay, so far let us come back to this topic of theorem proving. And if you remember, we had these basic notions of entailment, which says that a knowledge base entails a formula alpha, and then we had the notion of proof, which said that a knowledge base can derive a formula alpha, and then we had the notion of soundness and completeness. In particular, we are interested in completeness, which says that if something is entailed, then you should be able to derive it. The opposite is soundness, which is that if you can derive it, it must be true or it must be entailed essentially. Now, we have looked at two methods so far. Uh, we have looked at forward chaining, and what forward chaining does is that given a knowledge base of some facts. So, when you say facts, I mean true sentences, which in the sense of rule based systems means includes both facts and rules, but you can keep adding new things. And so on. So, in a forward chaining system, which is data driven, you have some thing in your knowledge base, you can make some inferences and you keep adding those inferences to the knowledge base. So, the knowledge base tends to grow essentially. And the hope is that eventually you will add the formula that you are looking for. If there was some formula called alpha that you wanted to show be true, that eventually that will be added essentially. That is the notion of completeness essentially. In backward chaining, you try to find rules which will make alpha true, which means you have things like uh, you try to look for rules of the kind beta prime implies alpha prime, and you try to unify this with this, and then have produce a sub goal beta, or you can have another sub goal beta prime prime and so on, depending on how many rules you have essentially. You try to work backwards from the thing that you want to show, and hopefully you will reach the set of facts that you have essentially. So, our example was you have man, Socrates, and man x implies mortal x, and the query was mortal let us say Socrates. So, in backward chaining you reduce this to man. So, if there is a query, you reduce to a sub query man Socrates, and this formula will match this formula here. In forward chaining you will add mortal Socrates at some point, maybe there are other things you could have added first, and hopefully when you add mortal Socrates, then you can terminate essentially. So, one advantage of backward chaining is low branching, and which is why very often people prefer to do things something like prologue, but we saw that in both the cases you may have to write the rules carefully essentially. Now, let us look at a couple of examples which show that both these are incomplete. So, the first example is, consider this set of formulas on you have a very small knowledge base here. You have three statements. You are saying that A is on the table, B is on the table, and one of them at least is green. So, green A or green B essentially. And let us say our goal is to show that exists something which is on the table and which is green. So, first of all, let us call this formula alpha. We want to show that alpha is true. Alpha is a statement says there exists an x such that on table x is true and green x is true essentially. So, let us ask this question, is this the case? Is this statement entailed by the knowledge base? Does the knowledge base necessarily imply that there is something on the table which is green? The answer is yes, because we know that there are these two blocks and we know that at least one of them is green. So, this statement that there exists something on the knowledge base which is green is true, but unfortunately this is does not hold, cannot prove it. Irrespective of whether you try forward chaining or backward chaining, you cannot prove this fact essentially. In fact, there are hardly any rules in the knowledge base. In fact, the best you can try to do is convert this into a rule. You could say not green A implies green B. Okay, you could rewrite it as an implication and think of it as a rule, but it does not really help much essentially, because there is nothing to say that whether A is green or B is green or not. We know that one of them is green, but not both essentially. So, this is an example which illustrates that while forward chaining and backward chaining can work well in many situations, these are not methods which are complete. There are true facts which you cannot derive essentially. This example is from the book by Charniak and McDermott. The second example that I am showing you is from this our book that we are following, which is Brackman and Levesque essentially. So, that was example 1 and this is example 2. So, the example 2 is also, let us say, from a blocks world kind of a domain, and I have 3 blocks, let us say A, B, C, and I know that let us say this is green and this is not green. So, which of course I can write as a knowledge base on A B, on B C, green A, not green B. So, I have these 3 blocks which are stacked up, A is on B, B is on C, and I know that A is green and I know that B is not green, and my goal, let me call it beta, is there exists an x, there exists a y such that on x y, and maybe I should use the AND symbol directly, and green x and not green y. So, does KB2 entail beta? What is the query? That is there a green block sitting on top of a not green block? So, is it true or sorry?
Not green C, KB.
Not green C. So, A is green, C is not green. Luckily, I drew the figure. I think so. And I want to show whether there is a green block which is lying on a block which is not green essentially. In fact, Brackman and Lewis use this example to show that entailment sometimes is not so obvious, but if you give it a little bit of thought, you will see that this statement is indeed true, because there are 2 possible cases. One is that either B is green or the other is that B is not green. If B is green, then B is on C and B is green and C is not green. If B is not green, then A is on B and A is green and B is not green. So, the statement must be true essentially. Again, it turns out that we are not able to derive it essentially, and maybe you can just give it a bit of a try essentially. So, this gives us a motivation to look for another method, and we have already seen this method, except that we saw it in the case of propositional logic, and it is called the resolution method. So, just to highlight this fact, let me just work with these 2 examples to start with, and then we will go through the details of revisit the algorithm in a little bit more detail essentially. So, let us take example 1. What are the facts given to us? On table A, the other fact given to us is on table B, and the third fact given to us is that one of them is green. So, you might recall that the resolution method requires things to be in conjunctive normal form, all the formulas. In this case, all these 3 formulas are already in conjunctive normal form, they are very simple formulas. So, we can work with them directly. We will see later on, we will revisit the method of converting them into this thing. So, these are this is given to us, and the goal is that there exists x on table x and green x. So, if you remember the resolution refutation method, we negate it So, which means we get this formula, or let me use the original color now. So, that to suggest that this is what you are working with. So, if you remember, the resolution refutation method said that you negate the goal and add the negation of the goal to the set of facts or the set of formulas that you have, but we must first convert it into clause form. So, to convert that into clause form, we know that this is equivalent to for all x, I will push the not inside twice in one step, not on table x or not green x, which when I convert into implicit quantifier form, I get this not on So, that is the fourth clause that I add to the set. And now, I want to show that this set of 4 clauses that I have is unsatisfiable. And if you remember that in the resolution refutation method, it amounts to being able to derive the null clause essentially. So, how do we do that? So, let us resolve this with this first. We have already looked at unification. So, we will need to apply unification to make the two formulas true. So, you can see that this not green x we can match either with green b or green a, it does not matter. So, let us say we say that x is equal to b, then we will get not green b here and not on table b here essentially. So, when we resolve these two clauses, we will get not on table b or green a. Just let me know if I am making any error. In a similar fashion, we can also say that x is equal to a, and we will get not on table a or green b. Now, using this and this one, because on table a there we get green b, and if I use this and this by saying that x is equal to b again, I will get not green b, and then from this and this I will get the empty clause essentially. So, this is one way of deriving the empty clause, but you see that we were successful in deriving the empty clause essentially. And this is something that we could not prove either using forward chaining or backward chaining essentially. So, I will leave the second example that I gave, which was the 3 stacked up blocks, as an exercise for you to work on to show that it is it can be as shown in the repetition method essentially. So, one thing that we need is to convert formulas into clause form. And when we say clause form, we essentially mean that the form should look like this: for all x x1, for all x2, for all xn, and then there should be a CNF formula here inside. So, this particular form is called a clause form, where there are only universal quantifiers and they are all outside to the left, and inside the bracket we have a formula in conjunction oval form. There are no quantifiers inside, there are no implication signs, there are no equivalent signs, only the CNF form and, or, and not, and everything should be in that form essentially. So, one of the first things we need to do is to convert formulas into clause form. So, let us look at a way of doing that essentially. What is the algorithm for converting So, first step is take existential closure. So, which basically means that if x is free, then introduce there exists an x, because we want to talk about sentences, and we said that formulas with free variables are not sentences. So, we will first convert it into a sentence by saying that whenever we have a formula like with a free variable. So, if I say x is greater than 13 for example, then what I really mean is that there exists an x such that x is greater than 13. So, I will just add a existential quantifier for that particular variable essentially. Then we have already seen this standardize variables apart, because one of our goals of converting into clause form is that we do not want to handle quantifiers. So, once we have it in clause form, and since all the quantifiers are outside the square brackets, you can just throw them away actually. But if you do that, we have to be careful that that whenever we use two instances of the same quantifier, we must use a different variable name, and that is what we had said when we were looking at forward chaining as well. 3 eliminate all connectives, and we have seen that how to do that for example, and we will see another example. So, implication can be P implies Q can be replaced by not P or Q, P equivalent to Q can be replaced by P implies Q and Q implies P, which in turn can be replaced, and so on and so forth. You push the negation inside, because we have seen that negation can create havoc for example, with the nature of variables essentially. So, if you have formula like there does not exist x which something something, then you should push it inside and convert it into a for all x formula essentially. push the quantifiers also inside next. So, the scope of each quantifier is as tight as is it's needed. This is again good for clarity. Eliminate the existential quantifier essentially. So, this we have already studied. This is the process of Coulomization. How to eliminate existential quantifier. So, if you remember that we replaced it either with a every existentially quantified variable, we either replace it with a Coulomb constant or with a Coulomb function of a universally quantified variables essentially. We will maybe see an example. Now that you have eliminated the existential quantifiers, you can bring all the universal quantifier signs outside without changing the meaning of the formula essentially. Since we want it to be in a CNF form, we need to distribute and over naught. Is that correct? And over naught or over and? Anyway, I hope this is correct. So, we distribute and over or essentially, and we'll revisit it if necessary. Simplify. Sometimes you will find that you have redundant set of formulas, and you can simplify them to reduce the actual occurrences. And finally, rename clauses because you may end up using clauses again and again and again. It's best to rename all the different clauses with different variable names essentially. So, if you do this process, then you have ended up with a formula which is in the clause form essentially. So, in the next class I will start with an example of converting a formula into a clause form, and then maybe we will look at an example of resolution method again essentially, and if you have time maybe we will revisit the earlier example which we did not show.